Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. I'm sorry because today I have to make a record for you to study about Faraday's law. I'm really sorry because I'm under the weather, so I cannot directly to speak to you to discuss with you. I'm really sorry. But if you have a questions, I have attached my email in my slides, so you can ask me. You can send me your question in my email. Well, today we will study about Faraday's law. Talking about Faraday's law, uh, I hope all of you are having knowledge about this before when you were senior high school. Well, in today's tutorial, we will discuss what is Faraday's law and its practical implementation. The phenomena of electromagnetic induction was explained by Michael Faraday, who was belonged to England, and most of his work was on electromagnetism in 1831. After Faraday, Joseph Henry, who was belonging to America, also worked on electromagnetic induction. But the final details of this phenomenon was first time published by Faraday. To find this, he performed an experiment. He went to different corners on the opposite side of the ring and connect one wire with the input supply. So he observed that the variation of current in first wire also induced some current, and the value of current he found by using a galvanometer. This current production in the second windings was due to flux linking, and that was coming from the first windings. After that, he found some other effect, like he finds transient current in a wire when a magnet comes to the wire. So, in today's lessons, we will have a look at what applications and some other parameters of this law. So, let's get started with what is Faraday's law. So, Faraday's law states that when any conductor is placed in any varying magnetic field, the voltage will induce in the conductor. So, Faraday's law is the fundamental rule to explain the rule magnetic field in different electrical circuitry. In almost in in almost each and every electrical machine, either AC machines like induction motor, induction generator, synchronous motor, synchronous generator, or DC machines or DC motor, DC generator or transformer also follows the Faraday's law of electromagnetic induction. For a practical understanding of Faraday's law, sometimes we'll perform an experiment. So maybe in the given figure, you can observe that there are a bar magnet and a galvanometer. We move this bar magnet and see its flux variation and current production in the galvanometer. So, okay, where is the feature? Okay, I'm sorry, I forget to attach this feature. Okay, next we will talk about induced voltage and current by Faraday's law. For practical implementations of Faraday's law and how it generates voltage, we discuss some experiments that will clear your concept about the Faraday's law. Let's suppose that a wire is put in the field of a permanent magnet and joined with the galvanometer and the end terminals. This is like a closed loop arrangement. At the start, when there is no movement in the wire, zero value of current is shown at the galvanometer. Okay, if mood change the position of a loop from left to the right, voltage in just I'm sorry, I mean in just in the loop of current show on the meter. When we stop the loop, then the zero deflection at the meter. And then if we move loop from right to the left, then there is a gain current at the galvanometer, but now in opposite direction. The value of current produced depends on speed with which we move in the loop and its resistance. If we change the resistance of loop and then move it in the loop with same speed, then the value of the term remains same with the variation of resistance. So current multiplied by resistance equals to constant. It's the induced EMF, electromagnetic force, that cause to produce current in the loop. The value of current can be increased by doing some factors. The first, by increasing the strength of field. The second, moving loop faster. And the last is replacing wire with large no of turns loop. Now we do in this experiment, especially I mean same as this picture with a different way. Now we keep loop steady. Okay, now we keep loose static in a very the position of a magnet. Then there is ENF inductions in the loop and deflection on the meter screen. It's the relative motion among the magnet and the wire loop that generate the voltage induced in the loop. It's the value of flux that varies in the loop and produce electromagnetic force in it larger in the value of flux variation, then there will be larger electromagnetic force in just in the loop. So now we perform some other experiments, as you can see in the slide, for understanding of voltage induced. In this given figure, you can see that loop is uh, is linked with the galvanometer and bar magnet as placed near it. When the magnet is static, there is a zero current at galvanometer. It's, it it is donated as if as A in a figure, and when we move magnet toward the loop, then the current flows through the coil, and if you move away magnet from the loop, then there is again current produced in the loop, and it is denoted as B. You can see the difference with figure part A and part B. So also we can do another experiment for the current production by giving the value of field constant and varying the area of the loop. Okay, in the slide in figure A, you can see that the loop and field both are constant. In Then there is a zero value of a current galvanometer. Now, if we vary the area loop, then voltage induced the loop and deflections show on the meter. The voltage induced till the point that the distortion occurs in the loop after the zero voltage induced in it. If we again restore the loop shape in the previous stage, then there is again voltage induced in it. It's denoted by it's denoted as B in given figure. Now we given field fairly constant and loop area also constant rotates loop in the field, then there is a gain voltage induced in the loop and some deflection at the meter, as you can see on the slide. So it's the basic principle of a generator. Now we can see that another experiment in which we will see the how a flux variation in first coil induce a voltage in second coil. In given figure, you can see that there are two coils. First one is P. Okay, sorry. First one is V, and the second is S. The first coil is connected with the rheostat, switch, and battery, while S coil is connected with the galvanometer. Now if we close the switch of coil P and there is current, if value is shown in the galvanometer of the second meter, and then it comes to again 0 points. If we open the switch again, the current is shown at the second coil galvanometer. It's due to the flux variation in the S coil current produced. And the important thing is the current only produced when we open and close the switch. During this process, current in the first coil start from the zero to maximum, then maximum to zero. Then it flows continuously. This phenomenon of flux current generation due to one coil and second coil is called mutual injection. And the working of transformer relies on this principle. Okay, so maybe I will increase some explanations about it, that about Faraday's law applications. There are some applications of Faraday's law that are described here nowadays. So it mostly input in industrial machine and a medical equipment construction. The working of transformer follows the Faraday's law of electromagnetic induction. Generator also follow this principle, and then the induction cooler operation also relies on the working of Faraday's law. And the last is some musical instrument also follow this law, such as electric guitar. Okay, and next we will talk about Faraday's more about Faraday's laws inductions. When a magnet is moved toward, okay, we have a tree here, galvanometer. Okay, there is a really actually there are many applications about Faraday's law in our daily that maybe we don't realize that, but if you know right now the principle, maybe you can identify right now, oh, this one is uh the kind of example of Faraday's application. So that's that's why physics is a really important to learn, because application is really needed. The application is really needed. Okay, this is also the slide about Paris laws inductions, but in here we can see that when a magnet is moved toward a loop of wire connected to a sensitive, this is ammeter. I'm sorry. Okay, the ammeter shows that the current is induced in the loop, and here when the magnet is held stationary, there is no induced current in the loop, even when the magnet is inside in the loop. And then, and the last, when the magnet is moved away from the loop, the ammeter show that the induced current in opposite that's shown in part A here. And this one is a machinal electromagnetic force. Electromagnetic force. Okay, I'm sorry for this stop. Now we can continue uh, our our study. Okay, talking about machinal electromagnetic first, a counterclockwise here in structure is a counterclockwise current, as we call I, is induced in the loop, and a magnetic force on the bar carrying this current opposite demonstration. So actually, what is it emo- what is it now we will describe emotional electromagnetic force. Okay, in the straight, let's assume that a conductor is moving. Sometimes if you have a picture like now, maybe let's assume that conductor that with a constant velocity under the influence some external agent. So there are electrons are also described by electrification. The particle in the field can accumulate both of ends until downward magnetic force. So actually, there are more interesting situations when the moving conductor is a part of closed conducting path. Yeah. A more interesting situation occurs when the moving conductor is part is closed conducting path. So these situations is particularly useful for illustrating how a changing magnetic flux causes an induced current in a closed circuit. Okay, maybe for ENF, actually this Mr. Fahrin have explained clearly. I think because I also have watched your meeting also. So maybe we can move here in Lenz's law. In here also we can see that Lenz's law, the induced current must be counterclockwise to produce counteracting magnetic field directed out of the page. And as the conductor bar here slide to the right, and a magnetic flux due to the external magnetic field into the page stroke the area enclosed by the loop increase in time. Okay, if we talk about the Lenz's law, the induced current in a loop is in the direction create a magnetic field that oppose the change in a magnetic flux stroke the area enclosed by the loop. The loop. So that is the induced current tends to keep the original magnetic flux stroke the loop from changing. We can show that this law is consequence of the law of conservation of energy. And to understand Lenz's law, maybe we can what is it? Can see this slide that you can see this slide that a bar moving. Okay, here and the bar moving to the right on two parallel rays in the presence of uniform magnetic field. As the bar moves to the right, the magnetic flux through the area enclosed by the circuit increases with time because the area increase. And Lenz's law states that the induced current must be directed so that the magnetic field it produces opposes the change in the external magnetic flux. Because the magnetic flux due to an external field directed into the page is increasing. And the induced current, if it's opposite, this change must produce a field directly out of the page. Hence, the induced current must be directed counterclockwise when the bar moves to the right. Yeah, as you can see, when you move the bar to the right. Okay, actually here you can use the right hand rule to verify this direction. Maybe you can still remember when you were in high school. Use right hand rule. Okay, if the bar is moving to the left, is in figure B, the external magnetic flux through the area enclosed by the loop decrease with time. So the induced current must be directly counterclockwise when the bar moves to the right. Okay, let's examine these situations using energy consideration. So for suppose that the bar is given a slight push to the right, and the preceding analyze, we can found that this motion set up counterclockwise current in the loop. So what happens if we assume the current is clockwise, such that the direction of the magnetic force exert on the bar is to the right? This force will accelerate the rod and increase its velocity, which is in turn what case the area enclosed by the loop to increase more rapidly. Okay, so is the plate the plate enters or leave the field, the changing magnetic flux induces EMF which cause eddy currents. Actually, eddy current is what is it? Is one of um, lectures additional that you can study or not. But as I can see in slide of Mr. Fahrudin, I think there's no eddy current, but you also can find by yourself uh, what is it eddy current. Okay, this is this is one. There are maybe two problems that I have attached the solutions. Uh, I hope that you can study by yourself. What is it, the problem, and if you have a questions about the problem, please ask me. Please ask me freely. Okay. I'm sorry. Again, I say I'm sorry because I totally could not explain all of it to you today. But as I say, please ask me if you have a questions or a problem in this lesson. Yeah. Actually, I need a bed rest from the doctor. Uh, so I couldn't to sit maybe for 1 or 2 hours. I need to bed rest, so that's why I'm really sorry. So also I record this meeting in a bed in a bed. So yeah, good luck. Thank you for your attentions. If there is a weakness and mistake, please forgive me, and thank you for understanding me today. I hope that in the next meeting, I my conditions will be better soon. So we will meet in the next meeting. Okay, thank you so much for your attention, and good afternoon, everybody. Wassalamualaikum warahmatullahi wabarakatuh.